So in 2.1, we talked about graphing quadratic functions. So quadratics were x squared. In 2.2, we're going to graph polynomial functions. So polynomial is going to be anything higher than x squared, so higher degree functions. So two things we have to keep in mind about polynomial functions is that they are always continuous, meaning that they have no breaks, no holes, and no gaps. So they're continuous. So the example A on the left is an example of a continuous graph where B is not. So a piecewise function is not continuous. So polynomial functions are always continuous. And they are always smooth. So they have round turns. So continuous and smooth. Next page, we have an absolute value function graph. It has a sharp point here, so this is not smooth. So this is not a polynomial function. Cannot have sharp turns. The polynomial functions that have the simplest graphs are monomials of the form x to the power of n. So that would be something like x squared, x to the third power, x to the fourth power. These are just our basic forms of graphs. These would be what we called the parent functions, and then anything that's like added, subtracted, multiplied to it would just shift our graph or have a transformation applied to our parent function. So these are the basic forms. It says the simplest graphs. So these are just our parent functions. When n is even, so when we have an even exponent, the graph is similar to an x squared graph. When n is odd, so if we have an odd exponent, the graph's going to be similar to an x cubed graph. But the difference is the greater the value of n, the flatter the graph near the origin is. So if I had an x squared graph, that would be our basic parabola. But if we had x to the fourth power, it would just get a little bit flatter near the origin, kind of like this. There's a couple examples on the next page. We're not going to be graphing these using a graphing calculator. We're just going to be graphing them by hand. So in this section, we're not using a graphing calculator yet. We're just graphing them by hand. So on the next page, we have an example of an x squared graph and an x to the fourth power graph. So the higher the degree, the flatter the graph is near the origin. Same with x cubed. X to the fifth power has the same shape, but it's just going to be a little bit flatter near the origin. In example 1, I'm going to kind of not really focus on these as much. We're going to talk about more specific graphing strategies on the next few slides. But just to kind of get an idea of like what the graphs look like, if we had x to the fifth power, that's going to be the same shape as our x cubed graph. It'll just be a little bit flatter by the origin. What does a negative out front do to our graph? It's a reflection across the x-axis, so now our graph is going to look like this. If you want to plug in a couple points to see how wide your graph goes, we know that if we plug in 1, we'd get 1, or negative 1. So we'd have a point at negative 1, 1, and 1, negative 1, and 0, 0. So our graph would kind of look like this. You can plug in more points if you want, but it'd have this shape. Again, I don't want to focus on graphing these as much. We'll talk about other strategies in the next few slides. And then same with the x to the fourth power graph. That's going to look like an x squared graph. So it'll look like a parabola. But when we add one on the inside, which direction does that move our graph? Perfect. To the left one. So we would just shift our graph to the left one. Again, if you want to, plug in points to get a more exact idea of how your graph goes, but it looks something like this. So same idea when graphing higher degrees, they kind of have the same shapes as like an x squared graph would. X to the fourth power has got a similar shape. Next, we're going to talk about the leading coefficient test. This is going to give us a better idea of how to graph when we have like multiple terms. So with a higher degree of polynomial with multiple terms that come after it. So we're looking at our highest degree term. So if we have an odd exponent, so when the exponent is odd, so this would be like x to the third, x to the fifth, x to the seventh, whatever it may be. Then the end behavior of our graphs, so how it starts and how it ends, is going to be in opposite directions. The one on the left starts going down and ends going up. This is when A, so our leading coefficient, I'll say leading coefficient, is positive. The one on the right starts going up and ends going down, so this is when the leading coefficient is negative. So you can kind of think about it as if your leading coefficient is positive, your overall slope of the line, like if I connected these 2 points, my overall slope here would be increasing. So when your leading coefficient is positive, your overall direction of your arrows is going to be increasing. When your leading coefficient is negative, your overall direction of the arrows is going to be decreasing. Now when n is even, they are going to go in the same direction. So when your exponent's even, they go in the same direction. Think about it like an x squared graph. Your arrows either both go up or both go down if you have a parabola that opens up or opens down. So if A is positive, meaning our leading coefficient is positive, both of our arrows are going to go up. If our leading coefficient is negative, both of the arrows will go down when it is an even exponent. So example 2, we're going to be applying the leading coefficient test. So what we just talked about on that last page, we're going to apply it here. So we always look at our highest degree term. So that would be negative 4x to the third power. The rest of our graph does not matter. The rest of the function we can ignore. Is our exponent here even or odd? Odd. So are they going to go in the same direction or opposite directions? Opposite directions. And our leading coefficient is negative. So what does that tell us that our end behavior is going to be, Bella?
The one to the left is going to be up.
Awesome. The one to the left is up and the one to the right is down because they're going to go in opposite directions. Since our leading coefficient is negative, the overall direction is going to be decreasing. So if I connected these lines, it'd be like decreasing slope. For B, we're going to look at our highest degree term, so that's 5x to the fourth power. The rest of it does not matter. X to the fourth power is even, so they go in the same direction or opposite directions? Same. So are they both going to go up here or both go down? They'd both go up. Our leading coefficient is positive, so they'd both go up. Think about it if we were graphing a parabola. It would be a parabola that opens up when A is positive. Now what happens in between these lines is going to be some type of shape, but we'll graph that on the next page. It would be something happens in between these lines, but what we care about right now is just the end behavior. Last one for C, we have 2x to the fifth power. Our exponent is odd, so is our graph going to go, or our end behavior, is it going to go in the same direction or opposite directions? Opposite. Our leading coefficient's positive, so what does that tell us? Down and then up. Perfect. So the left arrow goes down, the right arrow goes up. Okay. So next we're going to talk about kind of what happens in between the end behaviors. So we're going to focus on finding the zeros of our graph. So the zeros are where we have x-intercepts, where we cross the x-axis. So if I had something like x to the 5th power, whatever my degree is, I'm going to have at most that many zeros. So if I have x to the 5th power, at most I'm going to have 5 zeros. So that means I'm going to possibly cross the x-axis 5 times. Sometimes these zeros could be imaginary. If they're imaginary, you don't cross the x-axis at that point. So we'd have at most 5 zeros. And then also, our graph is going to have at most n minus 1 turning points. So here we'd have at most 4 turning points. Which are the relative max or min. It's where your graph changes from increasing to decreasing. So you're not always going to have 5 real zeros and 4 turning points, but this is the maximum amount of zeros and turning points that we will have. Next page talks about the zeros of a function. So zeros, solutions, x-intercept all mean the same thing. If we're given a polynomial and asked to find the solution, it's the same thing as finding the zeros. We want to find the value where we cross the x-intercept, where our y is 0. Factors, almost the same thing, but factor is kind of like the one step before. If I have x minus a, that means x is equal to a would be a solution. So factor also is similar to it. In example 3, we're going to find all the real zeros. What would we do to find the zeros? We're going to set it equal to 0. And then what? Awesome. I'm going to take out the GCF. So it's negative 2x squared. When I take out negative 2x squared, I'm left with what?
X squared
Just x squared.
plus 1.
If I divide this by negative 2x squared, minus 1. Perfect. We could factor it more if you want to just solve from here, that's fine too. Let's break it down a little bit more. Can I factor x squared minus 1? What does it factor into? X plus 1, x minus 1. So now we're going to set them equal to 0 and solve. So here we have negative 2x squared equals 0, x plus 1 equals 0, and x minus 1 equals 0. So x is going to equal negative 1 and positive 1. What does x equal here? 2 zeros. Awesome. We have x equals 0 and x equals 0. You don't have to list it out twice, but when you're graphing, it's going to help us get an idea of the shape of our graph. So here we said that whatever our highest degree is, that's how many zeros we can have. So we had 4 zeros. And how many did I find? 4 zeros. I want to go to the next page before we actually graph this. And then we'll come back to this and finish graphing. So I'm going to plot these points on my x-axis. They're at my x-intercept, so I have a point at 0, a point at negative 1, and a point at positive 1. Now let's talk about our end behavior of our graph, how our graph is going to start and how it's going to stop. So if I have negative 2x to the 4th power, is my exponent even or odd? Even. So are they going to go in the same direction or opposite directions? Same direction. Are they both going to go up or both go down? Down. How did we know? Our leading coefficient was negative, so our end behavior goes down. So my left arrow is going down and my right arrow is going down. So out of my point farthest to the left, I put an arrow that goes down. Out of my point farthest to the right, I have an arrow that goes down. Now we want to talk about what happens in between these two arrows, what our graph looks like. So we want to talk about our multiplicity. So I had 2x equals 0. Because it was x squared, we have 2x equals 0. So I have a multiplicity of 2. And 2 is even. So does our graph touch and turn at 0 or go through? Touch and turn. What about at -1? How many x equals -1s do I have? 1. So I'd say I have a multiplicity of 1. Is 1 even or odd? Odd. If we have odd multiplicity, do we touch and turn or go through? Go through. And then same thing, we have x equals 1. How many x equals 1 did I have? 1. So I have a multiplicity of 1. My multiplicity of 1 is odd because we're talking about the amount of that number we have, which is odd. And when we have odd multiplicity, do we touch and turn or go through? Go through. All right, so let's apply this to our graph. So we're going to go through the x-axis at -1. What did we say we do at 0? Touch and turn. So I'm going to touch that point and turn. I don't cross the x-axis. And then at 1, we go through. So I'm going to go through the x-axis at 1. So my graph will look like this. To get a better idea or a more exact graph, you can plug in numbers in between your x-intercepts to see how high your graph goes. So here I'd probably plug in -1/2 and +1/2 to see how high or what our relative max would be here at these two humps, I guess you could say. But that would just be to get a more exact graph. How many turning points could we have here? 3 turning points. Here we actually have 3 turning points that we can see. We have a relative maximum, a relative minimum, and a relative maximum. So these would be our 3 turning points. So we can have repeated zeros. Repeated zeros help us with like the shape of our graph and the direction that our graph goes. So a repeated 0 is also called multiplicity. That's how many times that 0 occurs. So when I had x equals 0 and x equals 0, here I have a multiplicity of 2. When our multiplicity is even, so when you have an even amount of that answer, your graph touches the x-axis, or you can think about it as touches and turns, or some people say that it bounces off the x-axis. So when your multiplicity is even, meaning the amount of that number that you have, your graph touches and turns at the x-axis, but it does not cross the x-axis. When our multiplicity is odd, so when we only have an odd amount of that number, then we cross the x-axis. So let's go back to that last example and let's graph it. All right, let's look at example 4. We're going to do the same thing. We want to sketch our graph. So we can start by finding our, let's find our end behavior first. Yes. Yes. So we have 3x to the 4th power. X to the 4th power is even. So does that mean our end behavior is going to go in the same direction or opposite directions? Same direction. Are they both going to go up or both go down? Both go up because our leading coefficient's positive. Now let's find our zeros. What would I do to find the zeros? Set it equal to 0 and then what? I'm going to take out my GCF. So I want to factor. I'm going to factor out that GCF. We're left with 3x minus 4. Can we factor this anymore? Nope. So let's set them both equal to 0. X to the third power equals 0, and 3x minus 4 equals 0. X to the third power equals 0. How many zeros do I have? 3. X equals 0, x equals 0, and x equals 0. You don't have to list it out 3 times, but it may help when you're talking about your multiplicity and how your graph goes. And then x equals 4 over 3. So let's plot those points. So I'm going to have a point at 0 and a point at 4/3. So that's going to be 1 and a third. So it'll be there. Let's put our end behavior on the graph. So out of our point farthest to the left, we have an arrow that goes up. Out of the point farthest to the right, we have an arrow that goes up. Now let's talk about our multiplicity. How many x equals zeros do I have? So I have a multiplicity of 3. If my multiplicity is odd, do I touch and turn or go through? Go through. How many x equals 4/3 do I have? 1. So I have a multiplicity of 1. My multiplicity is odd because 1 is an odd number. And when we have odd multiplicity, we just said we go through. So I'm going to go through the x-axis at 0, and I go through the x-axis at 4/3. Now to get a better idea of how your graph looks in between this, you can plug in numbers in between 0 and 4/3 if you want. Plug in 1. See what your graph does, how low it would go. So this isn't an exact graph, but it is about what our graph would look like. What is the most amount of turning points we could have here? 3. We would have at most 3 turning points. So that's 3 either relative or maximums or minimums. 3 turning points. With our graph, I think we only have 1, but again, our graph could do something a little funky in between 0 and 4/3. So it may have more, but may not. 3 is the most amount of turning points we could have. So in part 2, we're kind of doing the same thing, but in reverse. So it's going to give us the zeros, and we have to come up with the polynomial. So we're going to do all the steps that we just did to find the zeros, but backwards. So it gives me the zeros. Next thing I want to do is put it in factored form. So when we put it in factored form, it's always x minus the number. So here I'd have x minus 0 and x minus -7. Well, I can write this a little bit better. X minus 0 would just be what? X. And x minus -7 would be x plus 7. And then to come up with our polynomial, we just have to multiply it out. So this would be x squared plus 7x. And then you always want to just name your function, put an f of x in front of it. So f of x equals x squared plus 7x. Let's do the same thing for the next one. So here, what would go into my factored form? X plus 4 and x minus 5. Then we just FOIL it out. So we get x squared minus 5x plus 4x minus 20. Combine our like terms. So x squared minus x minus 20. And then don't forget you gotta name it. So I'll just call it f of x. All right, 3 is a little bit different. Whenever we have complex numbers, they happen in pairs. So if I have a square root 3 as an answer, I'm going to have negative square root 3 as an answer too. So here we have 4 zeros. It's not stated that we have 4, but anytime you have a complex number, they happen in pairs. So complex numbers are square roots or i's. So if you have a square root or an imaginary number, you got to write its pair too. So when we write this in factored form, we have x minus 2, x minus square root 3, and x plus square root 3. When you multiply this out, you always want to start with the conjugates, the pairs that you have. And then we have a shortcut to multiply our conjugates. Start with the conjugates. Does anybody know what the conjugate shortcut is? A squared minus b squared. So x would just be our a, and square root 3 would be our b. So this would be x squared minus square root 3 squared. So x squared minus 3. Perfect. Square root and squared will cancel. You can FOIL it out. You'll get the same answer. It's just going to be more steps. If you have conjugates, which your complex pairs are always going to happen in conjugates, just use your conjugate shortcut. And then we're going to multiply this by x minus 2 and x. Next, I'll FOIL these two out, and then I'll just distribute the x at the end. I think distributing the x at the end is always just the easiest. So we have x cubed minus 3x minus 2x squared plus 6. And then I'm going to distribute the x. So x to the 4th power. I'm going to put it in standard form here too. So minus 2x cubed minus 3x squared plus 6x. So this is our function. Any questions here? Yes. All right, let's do 4. So we have a complex number there, so we need its conjugate pair. What's the conjugate pair of 1 minus square root 2? Awesome, 1 plus square root 2. So when I write this in factored form, I have x minus 4, x minus 3, x minus, I'm going to put it in parentheses, 1 minus square root 2, and x minus 1 plus square root 2. So I always want to start by FOILing out or working with the conjugates here, the pair. I'm going to simplify this a little bit. I have x minus 1 plus square root 2 and x minus 1 minus square root 2. Now you can FOIL, so you can multiply it out with your 3 terms, or these are conjugate pairs. So I can use my shortcut, a squared minus b squared. However, what's our a here? So conjugates are separated by the different signs. So we've got a plus and a minus. What do you think our a is? X minus 1. So we have x minus 1 squared minus, what's our b? Square root 2 squared. So x minus 1 is our a, because it's the same in both of them. And then x minus 2 is our b. Square root 2 is our b. So x minus 1 is our a, square root 2 is our b. So we've got a little bit more work to do when we do our conjugate shortcut here, because we have x minus 1 squared, so we have to FOIL this. So we get x squared minus 2x plus 1, and square root 2 squared would just be minus 2. Everybody with me so far? So we get x squared minus 2x minus 1 when we combine our like terms. Now the order that you multiply them in doesn't matter. You can multiply these two together next. I'm going to do that just because they're next to each other here. But if you wanted to, you can take your x squared minus 2x minus 1, multiply it by the x minus 3, and then multiply that answer by the x minus 4. But I'm just going to FOIL these together first. So we get x squared minus 7x plus 12. So now this answer has to get multiplied by the other answer that we just found. So now we're going to multiply these two together. So this is a little bit more work than just FOILing. Just make sure everything in your first set of parentheses gets multiplied to everything in the second. So starting with x squared times x squared would be x to the 4th power minus 2x cubed minus x squared. Then negative 7x times x squared would be negative 7x cubed plus 14x squared plus 7x. And then 12 times x squared would be 12x squared minus 24x minus 12. From here, we combine our like terms. X to the 4th power. We've got minus 2x cubed minus 7x cubed. So that would be negative 9x cubed. Then negative x squared plus 14x squared plus 12x squared. So it'd be 13x squared plus 12x squared be 25x squared. 7x minus 24x be 17, negative 17x minus 12. And then we have to name our function, so f of x equals this. We started off with, how many zeros did we have here? How many x equal? How many solutions? We started with 4, 1, 2, 3, 4. And then when we multiplied it out, our polynomial was x to the 4th power. Same with number 3, we had 4 zeros here, 4 solutions. So when we multiplied it out, we ended up with x to the 4th power. This is just one way that you can check your work. Here I had 2 solutions, x to the 2nd power. Same thing with 1. We had 2 solutions, so x to the 2nd power. So it's one way that you can check your work. Just don't forget about the pairs, the complex pairs. If you have i's or square roots, they always happen in their conjugate pair. And then when you multiply it out, it cancels out. The square roots will cancel. If you had i's, they'll cancel out, so you won't end up with i's in your original polynomial.